Hello, this is section 4.4 logarithmic functions. Objectives for this section are number one, converting between the exponential and logarithmic function, and number two, performing calculation involving logarithmic expressions, and number three, draw the graph of logarithmic function. So, logarithmic function, we start this section with a quick summary of the two topics from the earlier in this chapter. So, number one, in our discussion of the inverse functions, we learned that the one-to-one function, which is that function with the graph that passed the HLT, which is a horizontal line test, have inverse. Number two, the graph of every exponential function is a curve with a no change in direction that settle down toward a horizontal asymptote on one side, and the other sides take up the away from the horizontal asymptote. That is on the other side. A curve that passes the HLT, which is a horizontal line test. So together, these two statements guarantee that every exponential function has inverse. So definition: if x and b are, which is two letters we have, a positive real number, including p shouldn't be a 1, which is if the b is a 1 makes a constant function, and the logarithmic function with the base b. So we have a form of this one, but the last section we know how to convert this one to this one, right? So to get this, we just solve for y, but the log represent the y from the exponent, and then base b is the same b, and the x is the same x here. So find the inverse exponential function f of x equal to the x. So first of all, we have to have a function notation, and then we need to replace y, f of x with a y, and then interchange of x and y, and then solve for y. But in order to solve for y, we need to mention the y's from exponents, and then same 2 base here and the x right there. And then you can just put the inverse notations, which is inverse notations, so log base 2 of the x. So which means these are the inverse each other, and these are actually the same. Of course, these two are the same too. Okay, so f of x is the same as y, but once you interchange of x and y, and then it becomes the inverse function. So definition: if x and b are positive real numbers, including the b is not equal to 1, the logarithmic function with the base b, which is I introduced the equivalency on the top. All right, next page, please. So the goal for the next collection of the examples is largely to make sure that the equivalency definition above is committed to memory. So use the definition above to convert the following from the exponential form to the logarithmic form. So logarithmic form means we are solving for exponents. So logarithmic form means we solving for exponent. So once you have exponents on one side, other sides need to mention that the exponent, the whatever value from the exponents, that's why you have to use a log. So a is, exponent is a 4. That means we need to put the log because of 4 from the exponent. And then base is a 3 from the 4th power of the 81. The second one, same thing, exponent is a negative 4. The log base 2 of 1 over 16. Exponent 1 over 2. The log base 9 of the 3. Exponent is a 0 and log base 5 of 1. Okay, yeah. And then the next example, use a definition above to convert to the following from the logarithmic form to the exponential form. So in order to get an exponential form, which is, let's say this is equal to the dx, okay? So in order to convert that, which is now we need to find the base first. The base is always next to the log, which is this is the base. So put the 4, but other side of log is always an exponent equal to 16. Next one, same thing. I want to say this is an x. So base is a 2 to the x power equal to 32. The next one, let's say equal to 6. Base is a 9 to the x equal to 27. And then we can solve for x, of course. But this one, we just need to convert to the exponential form. Next page. So when working with a logarithm, the base can be written explicitly as was done with every example so far. However, there are two cases where the base is simply understood. So common logarithm, which means common logarithm means if there's a log with a base 10, you can just put down as log of x, 10 of x, okay? And the natural log means if you have a log but base e of x, you can just say ln x. So you need to understand what is a log by itself and the ln by itself. So example 4, use the definition of the logarithm function to convert the following form, logarithm form to the exponential form. So we know that log by itself means a base of 10, and then is a 1000. And then I'll show you how to actually easy to evaluate this one, okay? Because the meaning of the log is exponents, so base of 10. So if it's possible, I'm going to convert to the 1000 as 10 to the power, which is 10 cubed. And then in the expression, I need to look at what is the exponent, which is answer is a 3. So this is the answer actually. So log of 1000 means a 3. ln 1 means is a log of base e of 1. So this time actually if I'm matching it, so I want to say base e to the 0 is the same as 1. So I want to say 0. So this is the meaning of 0. But remember, the log with the base, log of the 1 is, any of the log with the base is going to be a 0. Same here too. It's going to be the log base e, and then this 1 over e is the same as e to the negative 1. And then is equal to negative 1. So always put the exponents, but make sure that you need to match this base. Match these numbers, okay? Once you do that, and then always that's equal to the exponent. Calculation involving logarithm, considering the expression 3 to the x equal to the 4, do you have any guess to what the value of x must be? Since the bases are same on the both sides, it is understandable and correct to assume that the exponents of x and 4 must be equal. Using this idea and the definition y equal to log of base b of x, which is equivalent to the b to the y power equal to x, we can evaluate certain logarithm. So next page, please. So we're going to evaluate the following logarithm expressions, which is I already showed you what it was, okay? So since we see the log that has a base of 4, so what I want to do is I'm going to convert to the 64 as a something, 4 to the something power. So which means I can say this is a log base 4, but 64 is the same as a 4 cubed. So the exponents I see is a 3. So answer is a 3. Same is a 2. But I don't think we can convert to the 8 to the 4 to the any power. But there's a common base, which is 8 is same as a 2 cubed. 4 is the same as 2 squared. So I'm going to replace those expressions. So instead of the 8, I'm going to put the 2 cubed. Instead of the 4, I'm going to put 2 squared. So this time, the base is a match, okay? But on the top here, actually the base for the bottom base 4 is 1. So this is actually the 3 over 1. Is a ratio between the two exponents, which is 3. But this time is you have a 2 and 3, right? So put the ratio. So it's a 2 over 3. That's the value of the log base 8 of the 4. Now consider an equation of the expression, the log base 7 of 23. But the problem is there's no way we can match these two numbers as the same base, which is I don't think I can write the 23 as a 7 to the something power. So as before, this evaluation can be interpreted as finding x for the log base 7 of 23 equal to x. And then using the definition with the exponential form, of course, this is going to be 7 to the x power equal to 23. But unlikely the previous example, neither 7 nor 23 can be easily rewritten to make the base the same on the both sides. If you can, let me know. In order to evaluate many logarithms, we will need the help of the calculator this time. So most of the calculator contain the following two logarithm button, which is this, which is a log, which is ln. So this is actually the base come with a 10. This is actually the base of e. So as mentioned before, these two buttons will calculate the logarithm of the base 10 and the base e respectively. So what about the logarithm of the base other than 10 or e, such as a log base 7 this time? So some calculator have the third logarithm button, usually something in the form as a log, and then you can put any base right here. As expected, this button will be allowed to calculate the logarithm for any base. But the most of case, the many calculators do not have this button. So the calculator I have, I can do it. So without that button, if you have a calculator that doesn't have a third logarithm button, you must memorize the following change of the base formula. So this is what we call the change of the base formula, which means when you have a log base b of x, which is, this is a b though, okay? So there's a typo error. So this must be a b. So which means you can choose any log, but you gotta get to the same log, okay? This and this is that. And then you split the x and b, but x goes on the top, and then the b goes on the bottom, okay? As long as you use that, and then we can do this. So the next one, so to calculate the log base 7 of 23, we can use the formula as that, as ln 3 over ln 7, which is come out approximately 1.61. Or you can use the log of 23 over base 10, right? Log of 7. And then you'll get the 1.612. So use your calculator to actually confirm that one, okay? So work with the calculator this time to verify the following calculations to round the two decimal place. So number one, so I'm using calculator, okay? So turn on your calculator. And then what is a log? So find the log, which is, my log is here. And then type the 0.001 and then enter. Okay, which is, okay, hold on. The log 0.001 and then equal, which is you said -3. And then same thing here too. I got ln 16. And equals is round to two decimal place, right? So I gotta say 2.77. The log of 16. I have 1.20. This time you need to keep the 0, okay? Because it's a two decimal place. Because after 0 is a 4, so you just drop that, whatever number after 0. But next one, I don't think I have a base 3 to type it in. Do you see the base 3 here? So this time choose ln or log. So this time I'm going to choose ln. So ln 29 over ln 3. So which is find the ln 29. And then divide by ln 3. And then you'll say about 3.07. Because there's a 5 after 6, I need to say 7. And the same thing here too, but this time I want to use a base 10. So log of 96 over log of 5. So log of 96 divided by log of 5. Which is I got 2.84. So those are the answers, okay? Alright, let's go to the next page. Graph of the logarithmic functions. We call the method we use to graph the exponential functions. So we gotta find for the exponential function, we need to have a horizontal asymptote and then 2 more points. The result was a curve with no change in direction and settle downward toward the horizontal asymptote on one side and then take off the way from the horizontal asymptote on the other side, which is I'm talking about exactly like here. So as you notice, the graph is actually increasing. On the one side, take off of the horizontal asymptote. So where's the horizontal asymptote? Of course, this is a horizontal asymptote. And then one of the this side is getting close to the horizontal asymptote. And then this is take off from the horizontal asymptote. So the graph has a horizontal asymptote at the x-axis. And the graph passes through the 2 points, which is 0, 1, and 1 and 2. The domain is a real number. But the range is, as you notice, the graph is always above the 0, okay? In this case. So recall that the g of x is equal to log base 2 of x, which is the inverse of the f of x equal to the x. As the inverse, the graph of f of x to the x, and then g of x equal to log base 2 of x will be reflection across the y equal to x line. That will the opposite characteristic describe the chart below. Alright, so when you take a look, okay, so f of x equal to 2 to the x power. And then g of x is, so these two are the inverse, okay? So I already put that as an inverse form. Of course, you can follow the step to find the inverse too. So asymptote is going to be the horizontal for the exponential, and then it's going to be the vertical. So whatever x was, and this would be y was, and this is going to be x was, okay? And then 2 points I have for the exponent 0, 1, which you got the 1, 0. 1, 2 becomes a 2, 1. So the inverse function means 2 points are always interchange each other. And then domain is negative infinity, infinity. Then becomes a range for the logarithmic function. And the range is 0 to infinity becomes the domain for the logarithmic function. So the graph of g of x equal to log base 2 of x will be as follows. A curve with no change in direction that goes downward. It is approached the vertical asymptote at the y-axis, and it gently increases as it goes up to the right. But first of all, I think I want to graph up f of x equal to 2 to the x, okay? Which is I already had it in the previous page, okay? So which means when x is a 0, 1, x is a 1 is a 2, x is 2 was a 4, and the x is negative 1 is 1/2 and 1/4 with the negative 2, right? So this was the graph of the exponential function. Now I'm going to put down the g function, but I said the two inverse function are always a reflection with y equal to x line. So this is y equal to x line. Going through the x and y are always same number. So this is y equal to x. So reflections. So I'm going to put the log. This time is a base 2 of dx, okay? So this time, but of course you can make a table if you want, but I'm going to use the point that I have here. So this is 2, 4, isn't it? So I'm going to interchange that as 4, 2. So 4, 2 is right here. Okay? And then this point is 1, 2, right? So I'm looking for 2, 1. Right here. And then this point is 0, 1. So I'm looking for the 1, 0. Right here. And then this point is negative 1.5. So half and negative 1. Which is right here. And this point is negative 2 and a 1/4. And then I put the 1/4 and negative 2. 1/4 and negative 2 right here. And then if I connect them, this makes the inverse of the function we have above, okay? So it's always what? Inverse each other. They are inverse, okay? So every logarithmic graph will be the single curve with no change in direction that will approach a vertical asymptote from the one direction and gently increase in the other direction. So let's consider the following three logarithmic function, which is we're going to graph later. F of x equal to log base 5 of x, and g of x is negative 3 log base 2 of x plus 1 minus 4, and p of x equal to ln of x minus 2 plus 1. So starting with f of x equal to log base 5 of x that has a vertical asymptote, which is x equal to 0, which is y-axis. And considering g of x is 8 times base b, and then the x minus 4, but I don't know how I wrote 4, but I want to put it as h here. So this must be h. So k would shift the vertical asymptote at the y-axis up and down, and then leaving the vertical asymptote at the y-axis, while a is, I'm talking about the letter of the general form, right? And then stretches or compression by the size of a. So a is a greater 1 is going to be stretched. A is between the 0 to 1 is going to be compressed. And the reflection when the a is less than 0. Okay, so leaving the vertical asymptote at the y-axis. So the only value of the g of x, which is I need to change the h, the k, that can be changed, the vertical asymptote is h that time. And then the altering the domain by the shifting the vertical asymptote left to the right. Okay, so determine the domain and the vertical asymptote here. So domain and the vertical asymptote for each equation. So that's what we're going to use for graphing later. Okay, so first one. Okay, so in order to find the domain is from the x value. So it's about this one. So you gotta set that is a greater than 0. That's all. I don't think we need to solve for x because it's really been solved for x, okay? So for the domain is 0 to infinity. Not even 0. You can't do that, okay? And then the vertical asymptote, even better. So in order to find the vertical asymptote, you just need to set this one equal to 0, okay, instead of the greater. Yeah, so that's all. So now in order to find the domain, you need to pull this, whatever next to log, okay, not negative 4, okay, negative 4 is about k. So domain is going to be set x plus 1 greater than 0, and so for x, which is subtract 1 both sides, x is a greater than negative 1. So which means what? Negative 1 to infinity. As a vertical asymptote, no, you just need to set x plus 1 equal to 0. And so for x equal to negative 1. So that's a vertical asymptote. For the domain, for the C, set x minus 2 equal to 0. Oh, the greater than 0. See? And add to both sides, x is a greater than 2. For the vertical asymptote, set x minus 2 equal to 0. And then so for x equal to 2. Alrighty, so we already know how to find the domain and the vertical asymptote. So next page, in general, logarithmic expressions are defined for only positive values, so solving an inequality can be an alternative way to find the domain of every logarithmic function. So example 7 again, determine the domain and vertical asymptote of each of the following logarithmic functions. So which means it's going to be the same thing as there. So I think I'm going to skip the 7, so I'm not going to do the 7 here. Alright, next page. It's going to be same as the other one. But I want to do the example 8 though, because it's a different problem. So determine the domain and the vertical asymptote. So this time, domain is from the 1 minus x. So 1 minus x set greater than 0. Always a greater than 0, okay? Because the log only contains the positive number. And then you just need to subtract 1 both sides. Negative x is greater than negative 1. But divide by negative 1. But when you're dividing it, you always reverse the inequality. So x is less than 1. Which means all the way to negative infinity up to 1. That's a domain. As a range, no, not the range. What am I talking about? So vertical asymptotes, yeah, same thing. 1 minus x equal to 0. So this time, I want to add x both sides. You can do that too. So 1 equal to x, same as x equal to 1. So this is a vertical asymptote for that function. Now that we can find the domain and the location of the vertical asymptote of any logarithmic function, because I showed you already. We can graph the curve by finding 2 points to determine which side of the graph will approach the vertical asymptote and whether the other side will be gently increasing or decreasing from the vertical asymptote. So graphing the logarithmic function will require two steps, which is set the domain and the vertical asymptote and then 2 points for the graph. So example 9. Graph each of following logarithmic functions. So we're just going to graph, okay? So first of all, but we need to find the vertical asymptote. So vertical asymptote for this case is x equal to 0, isn't it? So x equal to 0 is the y-axis, which is a vertical line through the 0. So which means it determines that what value you should use. So we only need the 2 points, right? So best point for this function is, I think I'm going to use the 1 and then the 5. Which means when you put the 1 is always equal to 0. But when you put the 5, equal to 1. So 1, 0. And then 5 and 1. 2, 3, 4, 5, and 1. Right there. And then behavior is going to be this way. It's not that. So slowly increasing, okay? Alright, next page. The G function graph. So vertical asymptote. So vertical asymptote, which is what? X plus 1 equal to 0. Which is subtract 1 both sides, x equal to negative 1. So x equal to negative 1, this is a vertical asymptote. Okay, and then this time, I think I'm going to use the 2 points as, I mean, you can put whatever point you want, but I'm going to make this expression is the multiples of 2. So in order to make a multiples of 2, which means I think I'm going to use the 0 first, which is a 0 makes the whatever base is going to be the 0 means a 1, which makes a 0, okay? And then I think I want to use 1 for the 1 plus 1 makes a 2, okay? So which means negative 3 times log base 2 of 0 plus 1 minus 4. which is a negative 3, but this is going to be a 1, right? So log of the base 2 of 1 is a 0 minus 4, which is negative 4. So I got 0 is negative 4, so 1, 2, 3, 4 right there. And then 1, I put negative 3 of log base 2 of 1 plus 1 minus 4. And then negative 3 of log base 2 of 2 is 1. Oh, so I don't need to write this, right? I can just say so 1 and minus 4. Right? So it's going to be negative 7. So when 1 is a negative 7. So there's a 4, 5, 6, 7 right here. So this graph is going to be the actually going up. So this is vertical asymptotes, right? So graph is gonna be this to go this. Okay. All right, the next one, the vertical asymptote is going to be set x minus 2 equal to 0, which is x equal to 2, right? So x equal to 2, so right here. And this time, table. Yeah, of course I want to use the 3 this time because x minus 2. And then, I don't think that's possible to make an e though. So, you can use calculator if you want anyway. So let me use maybe 5. Okay, so 3, so which is ln 3 minus 2 plus 1. So ln 1 plus 1, ln 1 is a 0, so 1. So 3 is a 1 right here. And then ln 5 minus 2 plus 1, but that one I have to use a calculator. ln 3 plus 1. So ln 3 and plus 1 is 2.1. So 1, 2, 3, 4, 5 is 2.1. So right here. So these are the graph pending. Alright, the next one, the vertical asymptote is 1 minus x equal to 0, which is x equal to 1, isn't it? So x equal to 1 is right here. And but the table for the 2 points, I think I want to use the I want to try to make the 1, so it's gotta be the 2, right? It's gonna be the negative 2? No. I need to make the 1, right? So yeah, I'm gonna say 1 minus x equal to I want 1. So yeah, 0. Sorry, what am I talking about? 0. So 1 minus 0 is a 1, right? So the 0 is a 1 number that I use. And the next one is a base 3. So I try to get the negative 2. Right? Because 1 minus negative 2 equal to 3. Because I try to match to the multiples of the base of 3, right? So 2 times log base 3 of 1 minus 0 minus 4. 2 times log base 3 of 1 minus 4. 2 times this 0 minus 4, which is a negative 4. So 0, negative 4. So 1, 2, 3, 4 right here. And then negative 2, 2 times log base 3 of 1 minus negative 2 minus 4. 2 times log base 3 of 3 minus 4. 2 times 1 minus 4, which is negative 2. So negative 2 is negative 2. Right here. So which means your graph will be going down to the vertical asymptotes. And then this is going to be going to this way, okay? Alright, yeah. So it's a curves. Alright. Yeah, that's all. Okay, so thank you for listening.